speak about these subjects, dipolar degree of freedom and the isospin equilibration processes in heavy ion collisions. And okay, I will try to, before start with the subject, to recall with some slides what are some of the physical cases we want to study in nuclear physics. And I start just with this phase diagram that surely is not cannot be plotted for finite system, but for very large system. But you see here that we can expect in a rather naive way that we have different regions that can be populated when hadrons interact. Nuclear at the ground state are in this point where rho 0 is the saturation density. We have rho over rho 0 equal 1 and temperature is equal 0. But we can, okay, with our accelerator, or in any case, we can imagine to excite this system and also to compress this system. And we can have, okay, hadron gases, condensed phases, also up to the quark-gluon plasma and so on. Why this picture could have some interest for us? Okay, because these are the density and the temperature which are involved in some typical astrophysical processes, like evolution of stellar objects, and also they are involved in some way in the first moment of the formation of a universe. And then this is, we want to get information on the interaction, nuclear interaction, just to understand better the condition of nuclear matter in this exotic condition. Really, I will speak about in a more limited energy region, which is the intermediate energy region, which goes more or less from, okay, 10 MeV per nucleon, okay, 40 up to 400 MeV per nucleon. In this case, we can explore a phase diagram that is much more limited, is smaller, okay, and we can imagine a typical process is the evolution, even if this is clearly is a static picture, okay, but at the time is we can imagine this trajectory when we do a collision or from a stable nucleus. We can go in a, for example, here where we are in a spinodal region in which the okay, the density is low, the temperature is finite, and we have instability, mechanical instability. In particular, we want to, as I told you, to know something about the nuclear interaction in exotic conditions. In particular, in the last decades, we concentrate in the study of nuclear symmetry energy. Nuclear symmetry energy is just the term of the total energy of a nucleus, which is proportional to this parameter, beta square, proportional to beta square, where beta is just the neutron excess with respect to the proton numbers. And it is very important to justify the fact that we cannot have surely stable nuclei with a large number of neutrons with respect to protons, okay? And why this is, we want to study this symmetry energy? Because still it is important in some time, in the some process concerning astrophysical object, such as the nucleosynthesis during the pre-supernova evolution of massive stars, and also the cooling of the proton and neutron stars. So, but obviously, what do? We do a reaction. We have accelerator, and then we have to make a collision with a very finite system. The collision I speak about are not the same like the previous talk, because we like to study this kind of subject with the nuclei which are heavier. So we play with some hundred of nucleon on average. So the many body problem is much more complex, and also the energy is higher. But anyway, we can have finite system. The system, more or less, we can divide our time evolution of all the processes in two parts. One part which is just the starting point and the first moment of contact of our nuclear slabs, and this is so-called the dynamical stage. In other words, is the pre-equilibrium stage. And after we have, after some time, we have the formation of hot slabs of nuclear matter, which can be treated more or less in a statistical way, according to the Niels Bohr hypothesis. The time are rather short in both the case. We have 10 to minus 23, 10 to minus 21 seconds concerning the pre-equilibrium, and also we can go also up to 10 to minus 15 seconds concerning the statistical decay, the secondary one. What is important to stress is that, for us, for our aims, the pre-equilibrium stage is the most important, because it's just in this pre-equilibrium that we explore the most exotic condition of our nuclear slabs. We can have a large density or very low density when there is a disassembly, and we have high excitation energy. And the second stage, has some importance, concerning maybe at the end concerning the structure, but concerning the time evolution for us, this is the most important stage. So these are the main problems that one has to solve in this energy region. We have a finite system of fermion which are strongly interactive. We need to describe many body correlation associated to the cluster production with high multiplicity, and if necessary, we have to use a new effective interaction. It's clear that when we use beam with 40 MeV per nucleon up to 50 MeV, up to 400 MeV per nucleon, we have a lot of clusters which are produced. And we have, obviously, we have time-dependent processes, and we need to separate these time regions, because this time, this time scale we are exploring cannot be measured directly, and we see in some way a convolution of all the processes. And obviously we need rather high efficiency multi-detectors, just because for us it's important to reconstruct completely the information, and with a good granularity, because we have a lot of particles which are produced. So I can show you what I have in Catania, the so-called chimera detector, which is a charged heavy ion mass and energy resolving array. And we have about 1,200 modules. Each module is practically a telescope of detectors, silicon and cesium iodide. And all the coverage is rather large. We cover about 94% of the solid angles. And we are able to use a different technique to identify particle. We use pulsed beam, then we can measure time of a flight, and we can measure velocity of a particle. Then if we have the energy, we can okay, measure the mass. We can measure the charge by measuring the specific loss of energy between silicon in the silicon detector, and also we can use pulse shape analysis in the cesium iodium scintillator to always to identify light particle. And okay, so these are typical identification matrix in which we see a lot of particle produced, and isotopes, okay, we can distinguish. So what is important now, okay, we want to study in particular symmetry energy, and what I can say is that, okay, a phenomenon which is closely linked, a phenomenon that is closely linked to the isovectorial forces, which sorry, this is okay, which generate the isovectorial forces generate the symmetry energy, is the well-known processes leading to the redistribution in momentum space of the charge mass excess of the emitted particle. So if we want to study isospin and symmetry energy, we have to establish more or less some state that for us is the equilibrated states. So we have a number of neutrons. The idea is to have a kind of a gas in which we have a number of neutron and a proton. And if the distribution of this excess is uniformly distributed in phase space, we are at the perfect equilibrium in isospin. And then we want to study the tendency of our system to reach, after the collision, to reach this equilibrium. And from this tendency, we want to learn something about the symmetry energy. What is important is that we have these difficulties, as I told you, and is the following. In the first stage, we can use dynamical model to describe our experiment. The dynamical model in our energy region are necessarily semi-classical model, and we use wave packet to describe the nucleons, and we introduce some correction to the semi-classical model to take into account the Fermi nature of our many body problem, and just to satisfy Pauli principle, but we use essentially semi-classical model. And this model are a many body approach in any case, and are able also to produce the clusters, okay? But this model cannot go up time very long, and after we have to apply a statistical model to describe our data. So we have two different approach. We have a kind of hybrid model, and each model has a proper dependence on the symmetry energy. So we have this, we can describe the global results, but we don't know how to, we have parameter of the symmetry energy in one model and in another model, but you can understand that this is not a good situation, because one model work with the density more near to the saturation one, and the first model work with the density at exhaustive value of this density. So just like to show you some example of this interplay between this pre-equilibrium effect that we have when we study a nuclear collision at this energy, and the effect of the statistical model. For example, the so-called sideward flow around the balanced energy. If I make the collision of a projectile on the target with some energy, there is some matter that is squeezed out, and this matter is mainly done by protons and neutrons, and then one can measure the quantity of momentum that is related to this sideward flow, normal to the beam direction, and one can study this sideward flow as a function of the rapidity along the beam axis. So if one assumes that in the first moment we have an attractive potential, we have this behavior, okay, with this linear behavior, and this comes from the dynamics model. Otherwise, we have, see, if we have a repulsion, we have this opposite slope. It is interesting to study this balance energy, try to understand how much is this, the balance energy when this slope change from negative value to positive value is an interesting quantity. But what happens after this very fast pre-equilibrium stage? We have this hot source evaporate particle and produce these signals. And so we are sensitive to the sum of these two contributions, and then the measurement of this balance energy becomes problematic, because we have this statistical processes with blur, with the mix our pre-equilibrium process, the effect of this pre-equilibrium very fast. So we tried to think to, this situation is more or less, there are some other example in which when one try to measure yields of fragments, distribution, yield distribution according to the charge or to the mass, or one can play with by making a ratio between this distribution, between this yield. We have always that this final result always depends from the statistical model, from the statistical decay at the end of our processes. So we tried to think to another observable that is nothing that the time derivative of the total dipole of the system. And we can suppose to have a good detector, and in fact we have this 4-pi detector are performant. So we can imagine to select some class of event in which, for which we are able to reconstruct all the information concerning the system. This means that we detect the total charge. We don't lose particle. We measure the velocity. And then we can construct this quantity. This quantity is nothing that the dipole of the system, which is measured in the asymptotic part of our reaction. And then, why this quantity is interesting? It can be shown in analytic way, but also by simulation, that because of the symmetry of the statistical decay mode, on average, this statistical decay is symmetric around 90 degrees with respect to the spin direction. Because of this symmetry, this average value is not affected by the statistical emission of the all produced source in a later stage. So we have a kind of self-averaging effect of this statistical effect, and clearly this quantity is closely linked to the charge over mass equilibration processes, and then we can expect that there is we have a dependence on the symmetry energy, on how we describe the symmetry energy. For example, this total dipole can be put in this form, where we have a kind of yield of different produced particle for each. This is an average value on a large class of events. And we have a momentum, and this is a correlation function. If we are in an equilibrium condition according to the definition the so-called the Rami definition, we have that this correlation coefficient are 0, and then that this quantity is 0. On the other hand, we can excite this dipole just making a collision with the proton, with the projectile and the target, which have a strong difference in the charge of a mass asymmetry. It's possible to estimate in a precise way how much is this quantity at the beginning of the interaction, and it is just proportional to the relative velocity and to the differences in the charge of a mass asymmetry. If I do a reaction, this is spontaneously, this quantities go to 0, the absolute value, is it looks like something like a damped harmonic oscillator, I would like to say. And oh, okay. How this? How? No. Maybe here. Okay. I can show here some calculation about this quantity is performed always with a constraint molecular dynamics approach, which is a molecular dynamics model in which take in account the fermionic nature of our problem. And this is, for example, a collision calcium 40 plus calcium 48. We have a large difference in the charge of a mass asymmetry between projectile and target at 45 MeV per nucleon. And you see this, okay, this is practically the first time derivative of the dipole. And you see this, this strong change during the first 100 Fermi over C. This means a time of the order of 10 to minus 21 seconds after heat stay constant. But in reality, if you want to look to the calculation, the system still evolve during this time, because we have secondary emission of a particle, the auto source cool, and so on. So clearly, when we have this dipolar signals which change in a fast way, we have also a gamma ray emission. So we can also, in principle, not only measure the asymptotic value here, but we can, in principle, also measure the gamma ray emission, and we can have also information on the time of the process. Really, this has been done at low energy, for example, in this system by comparing calcium 48 plus titanium 46 and calcium 40 plus calcium 48. By comparing the gamma ray spectra, we see an extra yield of this gamma around 10 MeV, which can be associated to this fast change of the dynamical dipole, which produces this extra yield. So, in principle, we have also the possibility to study the time. These are just an example of other calculation. Okay. Other calculation in which I show the correlation. For example, this is the density, or I do this collision, calcium 48 plus aluminum 27 at 40 MeV, and I can measure the density. Okay, the density change very fast and reaches some maximum value here, and after decrease because the system expand and so on. But the dipole, yes, change just during this the same short time. Okay, the average value. So if we study the average value, we really select exotic condition concerning the density and also on the energy of our system. The same also at the 400 MeV per nucleon, we reach still higher density here in a very short time, and this is just the time during which this dipole change. This is the average value, but if I use a model like a quantum molecular dynamics model, I can evaluate this dipole event by event. And if I don't take the average, I can see here for one event these oscillations, and that continues to oscillate because the dipole can be excited also in the fragment in a statistical way, okay? And after I have another event, and so on. If you can see here that there is a phase relation, and when I take the average here, I get a good value, but during the time, the memory is lost, and I end up with an average that is almost flat. This is the motivation of. So I can now show some experimental results about this quantity, and this has been studied in Catania. This reaction of aluminum 27 per calcium 48. And this is the quantity we tried to evaluate. We have reconstructed all the events with practically the total charge is the total charge of the system. And the total momentum is larger than the 70% of the detected total momentum is larger than the 70% of the total theoretical momentum. Also the mass is a large fraction. So we select a complete event in some way, just because we have this good efficiency multi-detector, and one can show this kind of map in which I show, for example, as function of the velocity of the particle along the beam direction, the charge of the particle. So we can, this this is a mid-peripheral reaction in which I have the projectile that still survives. Here I have the target, the quasi-target, and here we have a lot of particles in the intermediate region which are produced. This is can give you a global view of the process we are going to select. When one deal with this quantity and one want to evaluate this quantity, we have a kind of error. We could be random that that, for example, related to the resolution in the energy and so on. But because we are playing with the average value, this random uncertainty does not give us problem concerning the error, the error that can be very dangerous in a quantity like this are the systematic error. And we have evaluated by studying an auxiliary system, we have evaluated that the systematic error on this signal is rather small concerning the identification in charge. We can have some error, systematic error in the to identify the charge, especially for the fragment, the slower fragment, which stops in the silicon detector. But another point, delicate point, is the systematic error that I can have here in the velocity measurement. Really, we have hint that this error exists in some region of our detector. There could be some systematic error. Each instrument can have some systematic error. We have to calibrate every instrument also with respect to the zero, the systematic error. But for the moment, I show you instead the results related to reduced dipolar signals, which is nothing that the same observable, but here we substitute, instead of the the true center of mass velocity, the center of mass velocity computed from the velocity, from the measured velocity. In this way, I eliminate the systematic error. And in this case, we can have a good behavior of these signals. For example, there are some conditions that has to be satisfied. For example, I can expect that when I go to see quasi-elastic processes, this signals is almost the same like as the same value at the initial condition, that should be about 10 centimeters of nanoseconds, and this is a good condition. When I examine this signals for quasi-symmetric system, I get a smaller signals, and when this is a plot in which I in fact plotted this quantity as function of the charge of the biggest fragment. Then zeta equal 20 means that I have still a projectile. But if I go to more destructive reaction, more central reaction, I would like to say, this zeta b decrease, and the dipole, the average, this is a distribution of dipole, is not the average. We have a large fluctuation, but the average you can imagine is something like this, that goes to zero when I have practically destroyed the system. So it is rather sensitive. What is a problem is the following: when I do this trick, in some not trick, is this correction, I would like to say, I lose the invariance with respect to statistical model. then this is a partial result still. After, okay, I can show you here the final. The red point are just these dipolar signals, average dipolar signals as function of different window in the charge of the biggest fragment. This is behavior. And the black point represent the dynamical calculation with a different parameter concerning the symmetry energy. In particular, we find that is the best fit of this behavior is with the gamma equal 1. Gamma is nothing that the stiffness of the symmetry energy as function of the density. And also we have there is a very good sensitivity to this parameter, you see. And these are calculations that in any case are coupled with the statistical model calculation, standard statistical model calculation. So I go to conclude. What I can say that a further experimental investigation should involve a different system and different reaction mechanism. In particular, the next step forward in this kind of a measurement would require a more detailed investigation, including a reliable estimation or minimization of systematic uncertainty on the velocity of the charged particle. This would permit a direct measurement of the complete signal, of the total signal. Then we have recovered the invariance property. And for this purpose, longer measurement involving a target and projectile with the same charge and mass. If I do collision of identical nucleus, I have a symmetric condition, and then I can estimate the eventual systematic error on the velocity for some region of my detector. Okay, this is all. Thank you. What I have tried to show you is how much are important these pre-equilibrium processes in our fields. Okay, because we have this kind of problem. We have a mixing of different time scale. The range is 10 to minus 21, 10 to minus 15 is okay, is a lot. Thank you.